Hello, this is Dr. James Camp from Lee College in Baytown, Texas, and this is my thoughts on Chapter 1, Introduction to Computers and Programming, of starting out with C++ by Tony Gaddis. This is for an Introduction to Engineering class, but the same thoughts apply to any kind of introductory programming in C++. Okay, why program? This seems like a really silly question, and at the same time is a very fundamental question, because most of you at this point, if you're looking at this, you're looking at it on a computer screen. You're looking at it perhaps through YouTube, which is a program that is written. You may be looking at it through a YouTube app on your smartphone or tablet, which is a program that's already been written for you. The presentation itself was built in Microsoft PowerPoint, which is a program that's already been written for you. If there are all of these wonderful programs out there, why write your own programs? The simple answer is that a computer is a programmable machine. Part of what makes a computer useful is that we can write an infinite number of computer programs that will do an almost unlimited number of things for us. In fact, there are things that computers can do that they're theoretically capable of doing that nobody has gotten them to do yet. So all they need to be able to do that is a program, a set of instructions in the computer memory that the computer follows to accomplish a particular goal. And all they need for that program is for a programmer to sit down and write it. So you, as you are taking your first steps in learning to program a computer, are the bridge between what computers can do today and the almost unlimited number of other things that they can do potentially tomorrow. Without programmers, there are no programs, says the author of this textbook, and without programs, a computer cannot do anything. Okay, so let's take a step back from writing programs and just look at the system, the ecosystem that a computer represents that we're going to be contributing to as we write software. First off, the main components that make up a computer, there is a central processing unit, often called a processor, a microprocessor, or even just the chip at the heart of the computer. There is a main memory store. There is what's sometimes called secondary memory, or otherwise called long-term storage. There are input devices that bring information into the computer, and there are output devices that send information on to the user. Here is a look at some of the things that make up the ecosystem of a modern computer. You might notice, for example, that this computer has some typical input devices like a keyboard and a mouse. It has some somewhat atypical things such as a webcam here, a tablet interface, even a scanner for bringing in hard copy documents into the computer. All of this feeds into an internal interaction between the central processing unit and its memory. Those are constantly interacting with each other. And this information can be sent out to a secondary storage device, such as a hard drive or a USB stick, and it can be read back from those devices into memory and into the central processing unit. And at any time, the computer might be, the central processing unit might be displaying information on a variety of output devices, which include computer screens, so-called hard copy devices. Modern computers almost always have a sound card that can also display auditory information. You may even have software on your computer that can read web pages to you or something like that, so that the supplemental output of audio becomes the primary output. Okay. So the central processing unit, the processor, that is really the computer that we talk about. it has a control unit that receives instructions and an arithmetic and logic unit that arithmetic obviously refers to math. Logic refers to a specific kind of math that compares values and makes if, then, else decisions and or decisions. It makes logical decisions. Is this statement true or is it false? If it is true, what do we do? If it's false, what do we do? But those basic two sets of computations, basic math and logical computations, are what make a computer a computer. It computes the possibilities for a given situation, and what does that is the arithmetic and logic unit. And then once the control unit has directed the ALU to do its number chugging, its logical processing, it produces output which can talk to the rest of the world. Okay. The CPU is usually, in fact, almost always connected to a main memory source. Memory is volatile. That means as soon as you unplug the computer, well, unless it's a laptop with a battery, as soon as you cut power to the computer, that memory loses its values. The information stored in the memory vanishes. The technology currently used to make memory work is called random access memory. Random access is a computer term meaning that if I have a memory block and it looks like this, I can randomly access this point here instead of the opposite of that would be sequential access, where I have to start here and read across and then go to the next row and read across. Random access memory means I can pick this one memory location right there and read to it, write from it, etc. That's much faster than sequential access and enables the speed of modern computers. Memory is organized into bits. One bit is a simple 0 or off or false, or a 1, which means on or true. Obviously, you can't do a whole lot with zeros and ones, so we add them up. Traditionally, the basic unit of information in a computer was the byte, which is 8 consecutive bits. Okay, 2 to the 8th is the number of possibilities you can store with 0, 1, 8 pairs of 8 units of 0, 1 information. It's about 256 values. Again, that's not a lot. That will hold all the letters and numbers in the English language, so it's good for text processing, unless you go international, in which case you need more bits than just 8. And it can hold up to 256 values, but as an engineer, when was the last time you worked on a, say, physics problem where you capped off all the values at 256? You can't have any decimal points. You can't have anything other than the whole numbers 0 through 256. Not very useful. So today there's an additional level of information here called a word. Okay, and a word represents how many bits you can connect together to store one individual value. Most computers today are what we call 64-bit computers. That means their word size is 64 consecutive bits. That's 8 bytes. Okay, that's a huge amount of information. 2 to the 64th is a tremendously large number. You can hold huge amounts of information. We'll talk about the limits of current computer information storage in a future lecture. Each byte in memory is identified by a unique number known as an address. Some computers use word level addressing, where each 64-bit word has its own address and you can't break it down any further than that. But that wastes a lot of memory because, as I said before, if you're just storing English language letters, you only need 8 bits at a time. So most computers these days have the ability to support 64-bit words, but they also can break those down into individual bytes, and each byte has an address in the memory. This is a simple schematic of what main memory might look like. This main memory has a 10-bit wide by 3-bit deep data addressing space, which is completely false if you know anything about computers. Computers always think in powers of 2, so this would either be 8 bits wide or 16 bits wide, and then it would be however many layers deep as it needs to be. But just to help those of y'all who think in base 10, this is arranged from 0 to 9, and then 10 to 19, and then 20 to 29. Memory is split up into these locations. Again, we're pretending right now that each of these locations is just a single byte. So you can store numbers like 149 or 72. You could store the letter A at location 13. You could store, starting at 1, you could go the letter H, E, L, L, O, and you've stored the 5 characters necessary to say the English word hello. We would, in computer science speak, we refer to this as a string of text. Okay, it's a string of characters that represents a single unit of text. Secondary storage, sometimes just called storage, is non-volatile. That means when you cut power to the computer, the data is not lost. Historically, the only data medium that had the ability to store information when the computer was off was magnetic storage. You could pieces of thin metal or tape material, metallized tape material, could hold magnetic north and south poles as if they were ones and zeros. And so you could write to the very first of these media was simply reels, long reels of magnetic tape that you ran through a computer, and as the computer spit out data, it would write it to that piece of tape. And if you wanted to read that back, you had to roll through the entire tape until you got to that one point and read it. Obviously, that's that sequential access we talked about. That's not ideal. So they developed something called a hard drive, which has a circular plate, sort of like a CD-ROM or a DVD, about that size maybe, but made of a solid piece of metal. And as it spins, a head can move back and forth across it and randomly access individual points on that that metal plate and read or write, again, magnetic signals that hold their magnetism even when the power is off. They made small versions of these called floppy disks. You may or may not have ever seen a floppy disk. These days they're in short supply. But they were hand-sized or pocket-sized. You could carry them with you from one computer to another. They did not hold tremendous amounts of data, but and they were not terribly sturdy. The word floppy meant that the media was not a hard plate like a hard drive. It was a floppy piece of film, and as such, it was very easy to accidentally sit on your floppy disk or step on it or somehow crunch it in a way that made it suddenly unreadable, and you'd lost perhaps your whole research paper by accidentally crunching your floppy disk. Recent advances in solid state technology have made it possible to have memory chips that don't lose their values when they lose power. You've used this any time that you've used one of those little USB sticks that are now ubiquitous. Everybody carries a USB stick around, or at least they could if they wanted to. You can get them in your drugstore. And at first, these held relatively small amounts of data themselves, but now you can store 16 gigabytes of information on a stick that you can add to your key ring. That's enough to carry the entire Windows operating system, or the entire Mac operating system, or entire an entire movie worth of high quality HD film, video around on one of these. They have no moving parts, so they are actually not just faster, but also sturdier. There's no metal plate that can crash against a reading head or anything like that that would damage this. There are also optical media. CD-ROM was the first, then DVD-ROM. There's been some attempt to create a Blu-ray ROM, but with the advent of, as I said, 16 gigabytes stored on a USB drive, there hasn't been that much interest in creating a rewritable Blu-ray. And really recently, the same technology that makes your USB sticks work has been used to replace traditional hard drives with what are called solid-state drives, little sticks of memory that fit onto your computer and can store up to gigabytes, up to terabytes. I have a 1 terabyte solid-state drive in the computer I'm recording this on right now. Input devices send information to the computer from the outside. There are a whole slew of devices we've invented that can provide input. Keyboards are typical for inputting text. Mouse is typical for user input with clicking buttons and such things. Lately, touch screens have become very popular, but there are also tablet devices that you can use to draw on to send higher resolution pictures to the computer than you could get by trying to draw with a mouse. Digital cameras, everybody's cell phone these days has a digital camera as part of it that can provide input to your computer. And of course, most computers now have a microphone, otherwise I wouldn't be able to record this video for you. Disk drives. CD drives, DVD drives, these are not really input devices, they're storage devices, but since you can carry them from one computer to another, they can provide input to that computer. Output devices then are devices that the computer uses to send information back to the user. Some typical output devices are the text-only terminal. For a long time in the history of computers, this was the most interactive output you could get from a computer was what looked like a small television screen with lines of glowing text across it. Nowadays, when we write C++ programs, we often generate a little window that emulates that terminal and provides text back to you, because it's very difficult for a beginner user, at least, to provide a graphical interface that makes the computer program not only work but look pretty. That said, almost every computer these days has a graphical computer screen that comes in any size from a 4-inch cell phone screen, or even smaller, a little smartwatch screen, up to you can plug most modern computers through their HDMI interface into a 72-inch television if you wanted to for output. It's also worth noting that there is a special category of output devices called hard copy devices. Another word for this is printers. A hard copy device produces something physical that no longer relies on the computer for its existence. Okay, so the most common hard copy device is a laser printer or an inkjet printer that prints a copy of a text or picture or something on a piece of paper. There are also hard copy devices called plotters that have essentially a pencil or a pen that moves in swirls on a much larger piece of paper to print, for example, blueprints for industrial manufacturing or architecture or something. And they've adapted those to have what are called plotter cutters, where instead of having a pen, you have a little X-Acto knife, and you can actually cut hard copy pieces of say plastic, out of a sheet of plastic. There are 3D printers these days that are not nearly the rarity that they used to be, where you can print one thin layer at a time and then add another layer and another layer and another layer and then ultimately produce a three-dimensional shape. And there are even hard copy devices that can machine a prototype part out of a solid piece of metal that have cutters and lasers and other such things, what we call rapid prototyping devices. So you can use a computer to make real world objects these days in almost any size and shape, and that's a pretty cool thing. Okay, returning to this idea of software running on a computer, the things that make a computer useful. Computers have essentially two layers of software these days. There's system software that manages the hardware and often serves as a interface between the hardware and the software you use. The most obvious piece of system software is called the operating system. That's Mac OS on an Apple computer, Windows on most PC computers. Some of us more hardcore computer files use a more advanced operating system called Linux that turns your computer into a high-performance software tool. However, there's less brand name software for Linux than there is for Windows or Mac OS, so most people don't use Linux for their everyday use. There are there's a reason I'm recording this video on Microsoft Windows and not on a Linux box, is that Windows has the PowerPoint software and Linux simply does not. Other things that fall in that system category are utility programs. You may have used a program to burn a file to a CD disk before, or to clean up your hard drive if there were a lot of scattered files that weren't being used anymore and you were running out of space. Or there are all sorts of utility programs that are out there. And then, of course, some people bundle software development tools like we'll be using in this class to write C++ programs into the system software. Really, it's an intermediate level that helps you develop either system software or application software. Most of the time, the operating system is pretty invisible to you, however, except when it breaks, and then you notice that it's there. What you usually use is the application level software, things that Microsoft Word for writing a paper, Microsoft PowerPoint for doing a presentation like this, Firefox or Edge or Safari for surfing the web, whatever email program you use, any games that you play on your computer, Minecraft, if you're into that, is an application software program. And then there are programs that solve very particular problems, which is the kind of program we'll be writing in this class, something that zooms in on one specific area of interest, maybe simulating a particular engineering part or solving a particular engineering equation. And that also is considered an application. Okay, so let's turn the corner briefly to programs and programming languages. A program is nothing more than a set of instructions that the computer follows, and a set of instructions constitutes what's called an algorithm. Okay, so you can define these sets of instructions at any different level. For example, if I wanted to program my kitchen robot to make me a peanut butter and jelly sandwich, I might define it at the level of get out the bread, add jelly, add peanut butter, put the two pieces of bread together, put it on a plate, cut it in half. If the computer was sufficiently advanced to understand get out the bread, then that algorithm would work. However, computers generally aren't that advanced. Generally, they require very highly specific step-by-step instructions. So it would be open the pantry door, find the loaf of bread, put the loaf of, take the loaf of bread out of the pantry, put the loaf of bread on the counter, undo the twist tie on the loaf of bread, pull out one piece of bread, pull out another piece of bread, lay them flat on a plate. Then we go back to the pantry and we find the peanut butter jar, and et cetera, and et cetera. And that's the level of thinking you're going to have to get to be able to program a computer, is to break things down into very small, very simple steps. An example algorithm for calculating somebody's pay. Now this is fairly silly, because it asks the person to tell you, how many hours did you work? How much do you get paid per hour? Well, shoot, I get paid $50 an hour. I don't know about you. So nothing would really work this way. You'd really have a file on a disk somewhere that had recorded what that person's pay rate is supposed to be, and an interface with a clock in, clock out system that figures out what their actual hours were. You wouldn't ask the person to just self-report how many hours did you work and how much do you think you should get paid. If the world worked that way, it would be awesome. But this algorithm, a really simple one, display a message on the screen asking how many hours did you work. Wait for the user to enter a response. Display a message on the screen asking how much do you get paid per hour. Wait for the user to enter a response. Multiply the number of hours by the amount paid per hour. Store that result in memory. Display a message on the screen that tells the user how much they should get paid. Okay, and we're going to be revisiting this program through the rest of this presentation as a simple explanation of how this works. Now, the previous algorithm is in what we would call English language, or natural language coding. No computer at present is able to understand natural language code and just do what we just said. In fact, almost every computer at present reads what's called machine language, which is a series of ones and zeros that might look like this. The first half of this might be a machine level instruction that says read a number from memory, and this second half of that code might be the place in the location in memory. This would be using 8-bit addressing, so very small amount of memory. But that might be the location in memory where we would look for the number that we're trying to read or write. Most people don't write programs like this. Okay, programmers would much prefer to write in what's called a high-level language, which is a language that is closer to readable English. Okay, nobody has achieved a high-level language that really reads like English yet, but that's sort of the holy grail for computer programming, is to someday come up with a natural language programming language. So a little terminology there that I just snuck in. Low-level languages communicate with the hardware directly. They can be written in binary machine code directly, as we saw on that last page, 1010111, or they can be written in what's called assembly language using something called mnemonics, which often have 3-letter or 4-letter codes like MOV for move, move a value from one place in memory to another place in memory, add the numbers that are stored in these 2 places in memory. But you have to break things down into very simple instructions. You can't even, in a programming, in a low-level programming, you can't even say A equals B plus C. You have to move B into a location, C into a location, add them, store them as A. Okay, so breaks down even very simple, what we think is very simple instructions, into even simpler ones. High-level languages are closer to human language. That's where you could type A equals B plus C, or if A is greater than 10, do print A, or something like that. Okay, there are a number of high-level programming languages out there these days. Some of the best known are the C family of languages. I call them the C family because they all use similar, what we call syntax. They all have an if statement that looks the same way. They all have a while loop that looks the same way. They all declare variables the same way. So that would be C, who sort of started the C family, C++, C#, Java, took a turn in nomenclature and decided not to call itself C something, JavaScript, which actually bears very little relation to Java, but they came out at about the same time and picked the same name. But there are other languages out there. BASIC was an attempt to make a more human readable, more natural language kind of computer programming. It's led to Visual Basic, which is Microsoft's attempt to make it so that ordinary business people can program their computers, with some amount of success, I suppose. Python is another language that has tried to make itself a little more human readable. Fortran and COBOL, very ancient languages that one was aimed at scientific computation, the other was aimed at business. Ruby is a object-oriented language that's mostly used for web programming sort of things. There are more. These are not by any chance a comprehensive list of languages. You can, there was one that I learned in high school called Pascal that almost nobody uses these days. Languages come and go through time. Once we've written a high-level program, it's still in a human-readable form, and we have to compile it into a machine-readable form. In C languages, there are a couple of steps involved here. We have to run the program through a preprocessor to set up the code. Then we run a compiler to convert the code one line at a time into machine instructions. And then we run a linker that takes the various pieces of machine code that we've compiled that way and links them into one executable string of ones and zeros that can be sent to the computer's processor. Steps B through D can be, in some systems you actually run each step separately, but today they're usually performed by a single command typed in at the keyboard or a single button click on the IDE. And if you detect errors at any of these steps, it's an important point here, that will usually stop the process cold and prevent executing the following steps to get you to a executable program. Often this is an iterative process where you start running it, you discover an error, you discover an error, boop, you have to debug, and then you run it again and it gets a little further and it stops and you have to debug, and you keep running through this until you've caught all the errors and fixed them and you get a usable computer program. Okay. In the old days, you wrote your code in a simple text editor, something like Microsoft Word, but without all the fancy bold and italic and all those things, not even a spell check of any sort. You just had a blank screen and you typed your text into it. And then you went to the command line and you typed CPP for C++, and the name of the file you wanted to compile, and it would run it through and spit out errors as it found them, or eventually spit out a executable file. Today, and then if you wanted to debug, you had to run it in a debugging environment, which would tell you what's going on in your software at various steps, and it was a very involved process. Today, almost everybody writes software in an integrated development environment, abbreviated IDE. Okay, and examples of IDEs are Apple's Xcode, Microsoft's Visual C++, or the third-party sort of free software program called Eclipse. This is what one Microsoft Visual Studio's IDE looks like. It's a pretty good example of what a lot of the other ones look like. However, you have a list of your files here. You edit one of those files and it opens in a text editor, but this text editor has formatting and syntax highlighting. You can't see it from this screenshot very well, but because this is for some reason done in gray, but the word double would be in a different color from hours, rate, and pay, so that you see that double is a keyword in the language. It has spell check of a sort where it prompts you to correct things that it thinks might be misspellings, or it even has what's called autocomplete, where you start typing a variable name and it offers to complete it for you, which makes it a lot easier to use very long variable names. In the bad old days where you had to type everything in just a plain old text editor, people used very short names for everything. And that made code very hard to write, or very hard to read, rather. Today, you can use 20-letter variable names, and with the autocomplete functions in your IDE, it's pretty easy to write those, and then it's much easier for somebody to come back and read. Hours, rate, and pay are fairly short, but they're understandable. But if you had to also take out, tax rate, and you had to have pay before taxes and pay after taxes, it's a lot easier to just write pay before taxes, pay after taxes, than to try to shorten that into, PBT and PAT, and, okay, who knows what that means, right? So IDEs have greatly improved people's productivity with not just writing code, but being able to read other people's code and such and so forth. Once you run this, by clicking on the little play button here, it'll change the look of the window. You'll get a debugging environment here at the bottom that will show you what certain variables are doing in your program. You can, if you want to know how this calculation works, you can click here and create what's called a breakpoint. So when the program hits this part, it'll pause and you can read the variables, what hours is, what rate is. You click a button here and it will calculate the pay and show you what that is, and you can actually step through your code one line at a time if you want to find out where the source of your errors are, which is a very handy thing. Okay, so last but not least, what are the components of a software program? Here's a program that calculates somebody's pay. What did we include in that? Well, first off, the first building block of any programming language are the reserved words or keywords. These have a special meaning in that particular language, and they vary from one language to another. They almost all have some words like while and if, but they may define other reserved words a little bit differently. Keywords used in program 1-1 were pound include, which adds a library file, using, namespace, int and double, which are types of values, and return. You can see where those fall into place here. Pound include brought in a library. Using namespace told us what namespace we're using. That's a C++ concept. Int main sets up the main function and tells us what kind of value we're going to return at the end of it. Double sets up certain kinds of values there. Also in this program are library references. These operate like reserved words once the library has been imported into the program. In C++, we use pound include. Everybody uses it. Every language uses a different thing. It's import in some languages. It's using in other languages. It's pound include in C++. These are not part of the core language. Rather, they refer to special functions that have been coded for you by experienced programmers. The idea is that somebody else out there knows better than the average programmer how to make input-output happen, how to make math functions happen, how to make a random number generator, et cetera, et cetera. And so if you want to use these, you have to pound include those libraries. And once they've been imported, keywords like standard, cout, cin, inline, those are now added to the language, and they're library references. You'll notice that these library references are very short words. Okay, again, C++ was created back in the late 70s, early 80s, before IDEs with autocomplete became a common thing. So you had to type every character yourself, and it was much easier to type std than standard, much easier to type cout than console output. Okay, much easier to type endl than endline.
Just gonna lay down for a couple of minutes.
Okay, so programmer-defined identifiers are another layer. So we had reserved words or keywords, we had library references. Now the programmer gets to define their own identifiers. These are made up by the programmer. They're not at all part of the language, and they can be anything you want, usually within reason. I mean, you can't put weird symbols. You couldn't put emojis into your variable names, but you can put a string of text and say, you know, my very long variable name if you want. They're used to represent various things. The most common use of programmer-defined identifiers is to make variables that represent memory storage locations, but you can also write your own functions, you can make your own objects, etc. In program 1.1, we defined hours, rate, and pay. We inputted hours, we inputted rate, we used them to multiply by each other and assign the result to pay, we outputted pay. So we use these all as aliases for memory locations to store values and to store calculations. Which brings me to the idea of operators. Another component of this program were the input and output operators in C++. And we assigned a value that we calculated using the times operator or multiplication operator. The add, minus, times, and divided by operators work very much like you would expect them to for mathematical notation. So does the assignment operator. So you can see how those work in this. And this, one of the things that makes this a high-level language is that you can just write this equation out and have it work exactly like it would work on a mathematical notation. If you were to write that out on a piece of paper, you get exactly the same result that you would expect. Finally, programs have punctuation characters. Every statement in C++ ends with a semicolon. Sometimes you can have multiple things happen on the same line and separate them with commas. You'll learn the rules for those later on. Okay, all of these things add up to syntax. Syntax is the rules of grammar that programming languages must follow. And programming languages are much more specific about their grammar than the English language is. There are about 5 different ways to say certain things in English, but usually only one correct way to say them in C++. You'll learn rules for syntax as we go through the class. Variables are programmer-defined identifiers that represent memory locations. So if we had our memory here divided into several boxes, hours represents this first box, rate would be the second box, pay would be the next box, and that is used to access that box and store a value in it. Say I worked 42 hours last week, that would be hours equals 42, or cn to hours and I type 42 would be ways of dropping this 42 number into the memory box that's now referred to as hours. Okay, in C family languages, C, C++, C#, Java, JavaScript, A variable in a program must be defined, or another word for that is declared, before it is used. Okay, so we use a statement like double hours to define a variable. In C++, you can define multiple variables on the same line by using the comma to separate them. You may wonder where the double word came in from there. Are these values holding twice as many values as normal or something? No. There are many different types of data, which you'll learn about in this course. And the first keyword in a variable declaration tells C++ what kind of data you want to store there. So the word double here specifies that the variables hold what we call double precision floating point numbers. We talked about word size earlier. Back when word size was much smaller, we used single precision floating point numbers, which only held about 7 digits after the decimal point, which is not very good resolution when you're trying to store a number that repeats for long numbers after the decimal point. If you're holding 0.25, it doesn't matter. But if you're holding 0.33333333 or pi or something like that, you want longer, more precision. And so as memory got bigger and we were able to use a bigger word size, we doubled the precision of floating point numbers. And so double precision floating points are now used almost exclusively. Nobody uses single precision ones anymore because they're bad. They're low precision. So in this class, you'll almost always see us using double if we want to represent a floating point number. Incidentally, you may have never heard that floating point definition. Imagine scientific notation where you have 1.010101 times 10 to the negative 3 or something. That means that decimal point is effectively floating along that number with the times 10 to the minus 3 or times 10 to the 42 or whatever. And that's how computers store numbers with a decimal point in them, is that they store all the numbers after the decimal point and then a multiplier like scientific notation. Okay, finally, input, processing, and output. Programs follow essentially 3 steps. They gather input, they process the input, they produce output. Programming processes also follow a similar idea. You gather input about what your program is supposed to do. They say here you visualize the program running on the computer. I'm not sure I've ever visualized a program, but you use design tools like flowcharts, like pseudocode, which is halfway between natural language and C++, to create a model of the program. How is the program going to work? What is the algorithm going to look like? You might walk through your program one step at a time and try to think like a computer would think. Are there logical errors in here? Did I forget parentheses in my mathematical exploration so that it's going to divide by 2 first and then add 3 instead of adding 3 and then dividing by 2, or whatever? Then you're going to translate the code into C++, save it, compile it, correct those errors. Again, that's an iterative process. Run the program with test data, and that comes back here to checking for logical errors. If you hadn't seen an error when you pseudocoded it, you'll probably see the error when you run it with test data. You might input the number 3 and you're supposed to get out the number 5, but instead you get out the number 16. And you're like, okay, clearly I did something wrong. You correct those errors and repeat those steps over and over again. And then you validate the results of the program. After you've run it with several different sets of test data, you say, yes, my program works. And in this class, you then save the .cpp file where you can upload it to Blackboard, and I can look at it and say, yay. You also probably want to take a screenshot of your output to show that the program did work at least once, so that I can see that and see that you've run it and tested it. The very last topic in this presentation, and I'm not sure why it even belongs here, but we'll talk about it, is procedural versus object-oriented programming. Procedural programming, the focus is on the process or the procedures. You write individual functions that do individual things. Some people even write everything in one big main function and never bother to break it up into smaller functions. That's kind of bad programming style. It's better to break your program down into small reusable chunks, both for readability of the program and for what we call modularity, being able to, if I've already calculated how to turn a Celsius value into a Fahrenheit value once, I might as well save that as a function here that I can copy and paste into any other program that I write that needs to do Celsius and Fahrenheit, rather than having to hunt through my code to find where I did that one calculation. Object-oriented programming is an entirely different, what we call, paradigm for programming. Instead of writing discrete procedures that all operate in a particular order, you write objects that represent, to some extent, real-world objects. So the best way I can think of describing the difference between these is if I was simulating how a suspension system on a car worked. Okay, procedural programming, I would have a procedure, a C++ function for calculating the initial stress on that suspension system when I hit a bump. I'd have another C++ function for calculating how much it springs back and how much that springing is dampened by the shock absorber. And then I'd have a loop in my main function that repeatedly called that dampening and springing function until the thing stopped wobbling. Okay. If I were doing an object-oriented program, I would have an object called spring and an object called shock absorber, and I would send them both a message saying that they've been compressed, and then I would send them another message saying just simulate what happens next. And they would interact with each other. The spring would try to extend and the shock absorber would try to slow that down, and they'd interact with each other. Or maybe I don't want two objects for that. Maybe I just want one object called suspension system, and it models the interaction of those two internally. But the point is, with an object-oriented programming system, I send it one signal saying hit a bump, and it simulates the compression that happens when you hit a bump. And then I send it the object another signal saying simulate your response, and it will extend and then shrink and extend and shrink until it hits some sort of equilibrium, and it'll send that data back out to the program. Once you start to think in an object-oriented way, it's a much simpler way of writing computer software, but it initially is a little bit hard to wrap your head around figuring out what should be an object and what activities that object should perform, what your main program should do versus what your object should do. So we actually saved the object-oriented part of this class to the second half after the first exam. Okay. For the first half of this test, of this class, you're going to be writing procedural programs, and then for the second half, we're going to be developing an object-oriented simulation, like for a suspension system or for a rocket. Another example, perhaps, if I were firing a rocket into space, like SpaceX just did the other day, yay. A procedural function would have to calculate the thrust at each moment and the air drag at each moment, and adjust the position of the rocket at each moment, and just keep looping through all of those little calculations. Whereas if I just created a rocket object, the rocket would know its own thrust, it would know its own air resistance, it would, I send it a message saying rocket.launch, and it initiates, and then every second of simulated time, or every millisecond of simulated time is more likely, I send it a message saying rocket.fly, and it just calculates its next position as it's launching up into the sky. And like I said, it knows its own air resistance and its own thrust, and all those internal laws are programmed into it, so I don't have to, from the programming point of view, think very much about what's going on in this rocket. I just have to continue to simulate it 1 second at a time until I hit that point where, say, the stages are supposed to split, and then I call stage split, rocket.split, or whatever. So it works much more like a real world object, and that's why it's called object-oriented programming. Okay, so that concludes our first presentation on programming on the elements of a computer. Sorry this took so long, but I wanted to give you a good basis on the idea of how computers work and what it is you're going to be doing with this computer programming. Okay, you can stop here, or you can continue on to the Chapter 2 presentation on basics of C++.